I believe that if you do theory for theory's sake, you may end up working on problems that are not very relevant. And by keeping in close contact with experiments, it forces you to think about things that can be tested and measured. So this I have been doing all my career. Over the past, I would say 5 to 10 years, I have two main topics that I work on. So it always has been a spectroscopy of different kind, but now there are great advances in developing ultra-fast, intense X-ray pulses. These are done in big facilities like free electron lasers in Hamburg or in Stanford or in several other places in the world. And with these X-ray pulses, you can go to shorter time resolution, like attosecond. You can do diffraction, which means that you can probe structure with atomic specificity, and then you can also do many measurements of processes with high temporal and spectral resolution that is not possible with optical light. So like half of my effort focuses on X-rays, and I work not so much on interpreting experiments, but in predicting new experiments that can be done. These facilities are very expensive, and every experiment, it's millions of dollars investment if you get 1 week of beam time. So it's important to be able to design new experiments. My other area is doing spectroscopy with quantum light. Normally, people who do quantum light are people who are interested in applications like metrology or secure communication and so on, and they are not so much interested in the properties of matter. They want to get the best control over the light and to use it. People who do spectroscopy are interested in molecules or crystals, but they are not familiar with the quantum light, and so they work with classical light. And it's important to bring the two communities together in order to use sophisticated quantum light on complex molecules. So I have like half of my effort is devoted to studying the quantum optics literature to know what is feasible and propose corresponding spectroscopic experiments. What happened in science is that radio wave technology matured in the 40s, in the 50s, and so NMR is now very, very well developed. And throughout the years, sources of higher frequency became available, like terahertz, microwave, then infrared, visible, ultraviolet, and the X-ray. So it's part of a succession of developments, And the work in the other areas, like in NMR, are very, very sophisticated. They are doing things with control over phases and so on. And the state of technology of X-ray is much less developed. You don't have good mirrors, you don't have beam splitters and so on. So what I try to do is to learn from the experience in the NMR and in the visible, and to project things to the infrared, to the X-ray, in order to predict new experiments. I was always interested in light and spectroscopy, but what really brought me to this field is a school that was organized in Trieste. You know, in Trieste there is the International Center for Physics, sponsored by the United Nations. And then Alfred Kessler organized a 3-month school, winter school, on atomic and molecular physics and spectroscopy. And that gave me the opportunity to get to understand the state of the art and to meet people like Cohen Tanuji and Serge Haroche, who afterwards they also got their Nobel Prizes. And that opened up for me the open questions in spectroscopy. At that time, most work was done on atoms to do some clean systems, and doing spectroscopy and nonlinear optics with molecules was not very developed. And so that really what brought me into this field. Is one of the greatest rewards of being a scientist. And over the years, I have had many students and postdoctoral fellows from across the world, from Europe, from Germany, from China, from Korea. And I find teaching to be not a one-way street. You really learn yourself a lot by teaching, because it makes you think about things in elementary way, things that you previously took as granted. If you need to explain it to somebody, you have to think about this deeply and to really understand it. There are many fields that are fashionable, and this fashion changes with time. Something can be very fashionable in a few years and then disappears. And it's very hard for starting researchers to tell what effects are real and what effects are just some fashion that will disappear. So they cannot rely on their impression. They have to consult with teachers and knowledgeable people in their school in order to get some advice. And they can read for themselves and get a feeling. So the important thing is you want to work on something that is important, but you also want to do a meaningful contribution. So you can identify many problems that are very important and exciting, but you cannot do much about it. So it's a balance between having something important and something that you can contribute to. So When I was a student, I was fortunate that my advisor let me attend several schools, like this school in Trieste, and this is where you can get a feeling for what is going on. So I would say the biggest danger is to enter into a field that is just promising without substance. And this is something that you can avoid by talking to people, reading for yourself. For example, in my advanced graduate class on nonlinear spectroscopy, I let the students read many of the write-ups of the Nobel Prize. They have write-ups for each prize at 3 levels, something like a press release, and then a write-up for people who are not scientists, and then a more detailed write-up for people who are scientists. And all of these are written very well. They are very enjoyable to read. And I encourage students to read this, because then they can get a real feeling of what is meaningful and get like first-hand knowledge of recent progress. I started my PhD in 1971, and that was a few years after the laser was invented. The state of spectroscopy was very traditional. It was like fundamentally frequency domain spectroscopy, which means you use long laser pulses and you look at things in the frequency domains. And then the picosecond lasers came, and then people started to do time resolved experiments. And most people, since the technology was complicated, you were glad to have the pulse. So people were doing simple experiments like pump probe, nothing very sophisticated. And one of the developments that came during my PhD was the area of laser chemistry. It was a long dream of chemists to be able to drive chemical reaction in a new direction, that it doesn't do it spontaneously. So one of the first ideas with lasers was that a molecule, a laser can excite the molecule in a specific energy state and then induce laser-induced chemistry. And there were some of the experiments were related to do laser isotope separation, that you do multi-photon excitations and then you can selectively excite one isotope versus the other. But then after a few years of excitement, it became clear that when you excite the molecule with a laser, the energy first of all redistributes in the molecule, so it's like heating, and there was nothing specific about doing it with lasers. So that happens in the 1970s, in the late 1970s, and then the field died. But in 10 or 15 years, it was revived because laser technology developed so you can control the timing and the phases. You don't just shine a molecule with a strong laser and hope that something will happen, but you can really design the process that you want to look for. And right now, this is a very exciting field. Spectroscopy was changing very rapidly at that time, and quantum optics was just at the beginning, because once the laser came about, several groups, for example, Glauber had developed the approach of how to treat the quantum effects of light and doing photon statistics and so on. But all of these were very, very elementary. The resolution was not very high, and during the 70s, the quantum optics has been developed, and in the first phase following Glauber, in order to simply characterize the light, but nowadays you can use it in order to control what do you do with the light. If you use the quantum nature of light, you can control how it interacts with matter, and then you can get access to new phenomena. Some of the experiments that are available now are called multi-dimensional spectroscopy, which means you use several short pulses in order to vary the delays and get some nonlinear signal. These are techniques that exist in NMR, and in fact 4 Nobel Prizes were awarded in NMR for various aspects of this multidimensional spectroscopy, and now it has been going up to the infrared, the visible, and most recently to the X-ray. This is a very active area. It is rapidly developing, and I think that no matter what, in terms of applications, there are basic scientific questions that are important and can now be addressed. One driving force for the quantum technology is things like quantum computing. Now, I'm not sure how long it will take to create a quantum computer, and there are many, many claims that remains to be verified. But what's important is the drive towards quantum computing stimulates a great progress in the area of quantum technology. You need to learn how to control coherence, and how to manipulate it, and how to measure it, and so on. So great science, I expect, will come even way before a quantum computer will be realized. But a quantum computer is a good flagship to follow. If you connect it to many-body physics, the information that you use in quantum computers is a many-body information. If you have a collection of ions that you excite coherently, the state of the entire system is what's important, not the state of an individual system. So that brings methods of thinking that you do in general to study many-body problems. And in fact, some of the applications of quantum technology is to create simulators of many-body physics. You create an artificial system that is much simpler than the actual system, but it can mimic by doing the quantum information on it. You can learn and you can mimic more complex physical problems. So I would say quantum technology is a sure thing to win because it can go in so many directions. And for example, people at Google have reported that they are able to solve protein structures by doing machine learning algorithms. This problem has been around for many, many years, and many attempts have been made to predict the structure of protein from, the three-dimensional structure of a protein from its chemical structure, but the success has been not very high. And this idea could really transform the field because you learn by handling a large amount of data, you can draw conclusions that are very hard to get in any other way. So this is just a recent example of a recent development.